Hello everybody, welcome back to Fastware. So today I want to talk about the disagreement that I had with my colleague. Disagreement stemmed from multi-threading and sort of a sheer lack of understanding of why one form of synchronization is superior than the other in a particular case, what causes that, how does it interact with hardware, how does hardware synchronize at all. So, and that sheer lack of understanding sort of scared me quite a bit. So I thought, how about I'm gonna create a video so next time if I will have similar disagreements, I will basically be able to point and say, look at the numbers. Since we're gonna go through all of it. So what we'll try to do is implement a mutex based queue. So a mutex synchronizing an access to a standard queue. And we will also try to implement an atomic ring buffer, which is basically just a vector of data, and you have access, or you control access to it via two atomics, a write and a read atomic. Both of them are fixed length, so it should be comparable. And as always, we will try to put it in a benchmark to see how it works. So let's get started. So the implementation of the mutex queue is fairly straightforward. We just have a standard queue. We control access to it via the standard mutex. And we obviously want to keep the size. So push pop are both more like try push, try pop, where if the conditions are not met, we basically exit early. So we control access by locking our mutex immediately at the top of the function. Next, we will try to set up our conditions, say what happens if we cannot basically insert anymore or push back. Say if the queue size is equal to the size that we want, we're just gonna return early. Otherwise, we're gonna push the element into the queue and then return. I think everybody can implement that. Now for the pop, it's exactly the same way. We lock that mutex and then we check that condition. If the queue is empty, we have nothing to pop, we just return empty, early, sorry. And then otherwise we just reassign the return argument res to the front, and that's pretty much it. So nothing up my sleeve. Very simple implementation. I think everybody can do that. Yes, obviously I have difficulty typing. As you can see, I need to correct some bugs. Now for the atomic ring buffer, the implementation is a tiny bit more complicated. So what we will try to do is set up this struct called align t, which is going to be aligned to 64 bytes. Now, I would like to pause here for a short second. Why do we need to align our element t, our single element, to 64 bytes? If you know, please stop the video right now, go to the comments and write it down. Share with the community that why this is. So I'm gonna give a few seconds for you to do so. I'm gonna continue and try to explain. So synchronization works on cache lines. It doesn't entirely work on single elements. Therefore, when you have your test data, as right at the bottom of the screen you can see the test data, which is a buffer of 70 bytes. That is more than a single cache line, which is 64 bytes. Now, if you just insert it like that, as it is, 70 bytes, that will occupy 1 and a bit cache lines. And then the next element will be occupying 1 and a bit cache lines, but they will be overlapping. So now the first and the second element will occupy 3 cache lines in total, with a bit to spare. That means when writing to the first and the second element simultaneously, because with the lock-free programming you can do that, what will happen is that writing the first element and the second element might override parts of the first element, because again, you write in cache lines, not in bytes, and a cache line is 64 bytes in size. That will result in paired writes, meaning that partial data can be overridden because it's coming from different caches, and you have data corruption at that point. Another reason why we do that is to avoid what's known as false sharing. False sharing is when a particular thread is associated with a cache which has its own copy of the data, and another thread has its own cache. That's a sort of a different view into the system. Now, when you're kind of reading from first one and writing to it, it needs to tell the other thread that the data has changed. So now that thread says, okay, this data has changed, and you have to invoke the entire memory infrastructure of a hardware to basically tell the other caches, hey, please invalidate your cache, we have data updates to this particular cache line. Now, when another thread tries to write it, it does exactly the opposite. And the cache line synchronization bounces between different caches, and memory subsystem is basically flooded with invalidate messages. Those invalidate messages are not cheap. The entire system basically stalls and waits for these synchronization messages to come through. So, false sharing can cause massive performance degradation to your system. So, to avoid that, what we do is we align our data to 64 bytes. We spend a bit more space to avoid performance degradation and also synchronization. So we implement our queue as a standard vector, and we have two atomic in 32 indexes, one for read and one for write. So we continue with the atomic block. Set up our read and write indexes to 0, and obviously we for our queue we just resize it to a fixed size that we care about. I think that makes sense, right? Now the way we implement push and pop is very similar. We basically get our read index, we load, and I'm going to be using the relaxed atomics. So we don't want sequential consistency because that can be quite slow in cases. Sometimes it's necessary, but so we're basically saying, oh, we want to get some data about the current read index, and we want to consume. We will be using the write index to update it soon, right? So we load those two atomics, and then we're getting our queue size, and we write this condition that basically if the current write index plus 1, so the next write index is equal to the size that we want, we just want to reset it back to 0, otherwise it's like that. Now, new write index is equal to read index, meaning you cannot push that index next. We want to just exit early, means our queue is full. Now, what we will do next is just write a while loop with a write index compare exchange weak, where we saying if this variable name for the write index atomic is at this value, which is the write index, updated to the new write index. And the memory orders is basically just read it or read and write. And then obviously if that condition in a while loop fails, we will be looping again, and new write index is updated every single time or recalculated every single time to what it needs to be. Other than that, this is very straightforward. So we obviously missed the not there, but I will update it in a second. So for pop is exactly the same way, right? We basically read the read index, write index, and then we say if read index is equal to write index, meaning we're either at the beginning or we already popped everything and there is nothing for us to pop. And then we do exactly the same thing for the read index, we just increment it and we use compare exchange week to do so. Now, want to stop here again and ask everybody, what is the difference between compare exchange weak and compare exchange strong? I'm gonna give you again a few seconds to think. Maybe open CPP reference for documentation. And anybody who knows, please write down your opinion in the comments below. Right. So, let me explain. Compare exchange strong is tend to be used with an if statement. It's sort of a try your best to make sure that this is correct. The compare exchange weak can spuriously fail if any other atomic operations or synchronization operations happened sort of in the periphery of this operation, right? At the same time, maybe by another thread. And therefore, it's much safer to just keep looping, even though read index will be updated to the new read index and we can always recalculate the write index. It's much safer just to keep trying quickly and fail quickly rather than do these more of a heavy-handed checks. So we run it in a loop, we're saying, oh, this is my expected read index, this is my expected new write index, new read index. Now, if the read index is not what it is, or some other atomic operation or synchronization operation happened, it's just gonna update that read index to, because it's passed by reference, it will just update it to the value that is currently stored in the atomic, and then it will fail. The new read index will be recalculated and will basically continue. Hope that makes sense. If not, leave the comments what you don't understand. I will try to explain it in a discussion in the comments. Make sense? So let's continue. So as usual, we just basically populate that result, remove the data, and we return. So I do not think that these operations are really difficult to implement. I'm sure you can all do it with a bit of practice. So as I said, we have a test data of 70 bytes. We have the basic test and the advanced text, which basically uses the two different queues. And we have the push pop tests basically running with a lot of threads. So obviously I need to fix my bugs since, you know, fat fingers, all that good stuff as usual. So that's done, and I think we should be good here, if I remember correctly. Yep. So what we'll do is just reformat our code, and let's look at our run. So here it is. Run our push pop, and we have some small amount of data. So obviously, as you can see, at 32 threads, we have quite a bit of difference in CPU time and even in application time as well. So what we'll try to do is run this benchmark with a lot more iteration. So we repeat 20 times, we run it for a long time, we want to return only aggregates. We collect all that data in order to make sure that what we've done, there's, no variation, that it's as close to what's possible. Try to understand what's the standard deviation between our runs as well. So the best way to understand this data is obviously to plot it. I like graphs, and they give very quickly an indication of what's happening. What I do is just set up my tables with the basic test data, their standard deviation, the advanced data. Now I just calculate the improvement by basically dividing the basic over the advanced. So I don't know if it's a separate tutorial how to use plotting tools, but I'm not gonna get into that. So what I do is just, make sure that I can visualize everything and understand. Also include the Y bar margins, which are basically the standard deviation. And let's stop here for a quick second. So let's look at that chart. So it starts very close, and we can look at the data above. We're on 2 threads. We're just over 2 times faster than the mutex using our atomics. However, as we go to 4, 8, 16, and 32 threads, that scaling, I mean, you can say anything, but the mutex does not scale very well, as obvious. So what I want to do is basically chart the improvement next. So let's do that. So we have the threads, we pick up threads and the improvement, and then we just insert another chart. So line charts show quite well this data. So here it is. Right. So let's look at it. From 2 times to over 5 times faster, from 2 threads to 32 threads. That is quite a significant difference. And if you're implementing the queues, which are high in contention, meaning you have loads of producers, loads of consumers, your best bet to use an atomic ring buffers. Because using standard queues will give you mediocre performance to start with. At the same time, you're scaling into kind of if you have a lot of threads, will be much worse than just a tiny bit more complex implementation. So I want to recap the concepts that we looked at. So we looked at atomics and relaxed atomics and why a lock-free programming in high contention environments are much better. We tried to understand what is or cache invalidation and how caches work a little bit. I hope that it will encourage you to go and read a bit more about it. Or we can have a discussion in the comments if you're care enough to ask questions there. Try to understand what false sharing is and how that introduced and why we need to align our data when we are in a lock-free programming scenario. So obviously, first of all, the alignment serves to avoid the write tearing, where you basically corrupt your data when 2 threads write into the same cache line. And also the false sharing, which impacts the performance. So I hope you learned a little bit something. And I hope you enjoyed it and was maybe a little entertained by my little tale. And if you liked, please leave that like. Subscribe if you haven't. Maybe this century will reach that 500 subs. And for now, thanks for watching. Take care now. Cheers. Bye.